The topic of this video is Eulerian graphs. We're going to start by talking about a historical problem, the bridges of Königsberg. This is considered the first problem in graph theory. And so this took place in the 1700s in Prussia. This part of Prussia is now in modern-day Russia. But there was a town called Königsberg, and this town had a river running through it, and it had 7 bridges that connected 4 different land masses. So we see sort of these 2 islands and one stretch of land on one side of the river and one stretch of land on the other side of the river. I hope you enjoy my drawing. So the question was, is it possible to walk through the city crossing each bridge exactly once? And if so, is this possible to do by starting and stopping at the same location, so beginning and ending your stroll in the same place, or by beginning and ending at different locations? And no swimming is allowed. You can walk around on the land and you can walk across the bridges. And supposedly this was a problem that the citizens of this town were actually trying to solve. So they would go on little strolls and say, oh, I didn't do it this time. I'm trying to do it, and this is the path I took. And then this is a problem that Euler looked at from a mathematical perspective. So I'd like you to take a look at this problem and think about whether you would be able to do a stroll through this city, crossing each bridge exactly once. And again, you could do it either by starting and stopping at the same place or by beginning and ending at different locations. So try this yourself, and you might want to model this as a graph. So can you model this as a graph? And if you do, what are the vertices of the graph and what are the edges of this graph? So take a pause, think about that, and we'll talk about it in just a moment. Okay, so let's think about modeling this problem as a graph, or actually as a multigraph. So we know a graph represents connections between objects. We see that the bridges are connecting pieces of land. So we could let the vertices be land masses, and we could let the edges be bridges. And in that case, our graph or our multigraph might look like this. So our graph or our multigraph might look like that. And we see that the vertices of this graph would be our land masses. This land mass could be our first vertex. B, this land mass could be our second vertex. C, this is another vertex. And D, that's the last land mass that's not connected to the rest, is our 4th vertex. And we see that these edges represent the bridges connecting these land masses together. So this first bridge is this edge from A to B, and so on. So I could start a walk or a stroll through this town, trying to go over every bridge exactly once. Let's say I started at A, the landmass A, and I went over this bridge first. There are different options, but maybe I go over this bridge next. So I've just come down into C, and again, different options. Maybe I go back, and then I head over to D, and then I could go back here. And now we see that I'm stuck. I have run out of bridges I could use. And no matter how you do this, no matter what sequence of bridges you take, you will not be able to cross over each bridge exactly once. In 1736, Euler proved that this could not be done. And moreover, Euler proved a more general criteria for describing exactly which graphs could be traversed in this way and which could not. This was considered the first paper in graph theory, and this was in fact done before any of the terms we've been using existed. So the term graph did not describe this type of mathematical object until the 1860s, over 100 years later. So he used a different type of language, but he did do an abstract drawing, kind of like what we see above. And I said, as I said, this abstract drawing, I mean, one nice thing that it does is it sort of simplifies the picture. Another thing that it does is allow us to think in a more general or abstract sense about which situations more generally would such a traversal be possible. So if the bridges were arranged differently, or the land masses were arranged differently, or maybe this even models a completely different problem, when can this be done and when can it not? So what I'd like you, so here's a definition. A connected graph is Eulerian if there is a circuit that visits each edge of the graph exactly once. Remember that a circuit, by definition, cannot revisit edges. In other words, a circuit cannot go over an edge more than once. So this part of the definition is actually a little redundant, exactly once. But anyway, a graph is Eulerian if the circuit contains every edge. That's the same thing in this case as going over every bridge. So my question for you is, which of the following graphs and multigraphs are Eulerian? So let's look at all of these graphs and multigraphs below. Which of these appear to be Eulerian? Which of these appear to have a circuit that contains each edge exactly once? So I'd like you to try these out, and as you're doing it, think about whether you can make any conjectures about a more general criteria of which graphs will be Eulerian and which will not. Just as an example, let's look at M1 together. So this is the multigraph M1. It's a multigraph because it has loops and multiple edges. So can I go through each edge exactly once? Let's say that I start there and I go and I've gone through this edge, and now I've gone through this edge, and this is a loop and I can go around it, and now I can go through this edge as well, and doesn't really matter, let's go this edge and then this edge, and I can continue, and this edge, and yes, I have done it. So I have gone through this graph using each edge exactly once and ended where I started. So this tells me that M1 is Eulerian. So try out with the other graphs. Try to figure out, is there an Eulerian circuit in these other graphs? And we'll talk about these in just a minute. Okay, so which of the following graphs are Eulerian? And can you make any conjectures about when a graph or multigraph will be Eulerian? So we already said that M1 was yes. We found an Eulerian trail through this graph, an Eulerian circuit through this graph. Let's look at K4, the complete graph on 4 vertices. So let's just say that we start here and go around. So we've used this edge. We can go up. We can leave that vertex either this way or this way, and we can go back up. Now we can go over, and at this point we are stuck. That doesn't necessarily tell us that there is no Eulerian circuit for this graph, but if you try a bunch of different ones, we can say we think the answer is no. So basically in all these cases, if we find an Eulerian circuit, then that tells us the answer is yes for sure. If we can't find one, so if we can't find an Eulerian circuit, that tells us we think not. But it could theoretically be the case that, we tried 1 or 2 and it didn't work, but there was one that we didn't try that does work. So, okay, let's try some other ones. K5, let's say that we start at this vertex. So let's say that we first start by just going around in a cycle. And now we could go this way, could leave here, leave here, leave here, and now we have ended back where we started. So yes, this one is Eulerian. Let's look at M3. Let's say that we start at this vertex. So we are trying to use every edge of the graph and exactly once. And we are going through, and then at this point we can either go down or we can go this way, and continuing. And now we have used almost all of them, but there is one missing. We didn't use that edge. So we think no. We think this is not Eulerian. We don't know for absolute certainty, but appears not. This graph G, let's say that we start here and use this edge, this edge, this edge, this edge. We can go in either direction. We see if we go up, we'll be stuck. So let's go using this edge. And now we see that no matter where we go at this point, after we do the next edge, we would be stuck. So we think the answer to this is also no. Let's look at H. Let's say that we start here. So we can go up, and again, there are different choices that can be made, but let's say that we're going along this circuit. In a circuit, again, we can reuse vertices, but we cannot reuse edges. So we're going along and going down and then going back up. And yes, we ended where we started. So yes, H is Eulerian. And last one, let's look at M2. So again, we can start anywhere. Let's start here. And we are using this edge, using this edge, using this edge, using that edge, going up, going around this loop, and going out. And yes, we ended where we started. So this appears to be Eulerian. So did you notice any patterns or come up with any theories about which graphs will be Eulerian? It turns out that the criteria is surprisingly simple. So a graph or multigraph is Eulerian if and only if every vertex has even degree. If we look above, we see that for example, K4, the answer was no. Every vertex had degree 3. They all have odd degree. All the vertices are of odd degree. K5, the answer was yes. In K5, all the vertices have degree 4. They are all even degree. If we look at M1, remember that loops contribute 2 to the degree of a vertex. So that vertex has degree 4. This vertex has degree 4 as well. This vertex has degree 2, and so on. Each of those vertices have even degree. M3, let's see, well, there's a vertex of degree 3, so not every vertex has even degree. Here's a vertex of degree 3, not every vertex has even degree. Here, all the vertices in this graph have either degree 4 or degree 2, all even degree. And same deal here. All the vertices here either have degree 4 or degree 2, all of even degree. So this is the first theorem in graph theory. A graph or multigraph is Eulerian. In other words, contains a circuit that contains each edge exactly once, if and only if every vertex has even degree. The degree of every vertex is an even number. Let's think about why this theorem is true. This is an if and only if statement, meaning that both directions hold. So if a graph or multigraph is Eulerian, then every vertex must have even degree. And if every vertex of a graph or multigraph has even degree, then that graph is Eulerian. So let's first think about the forward direction. And actually, this direction is fairly straightforward. So let's suppose that the graph or multigraph G is Eulerian. So that means that there is a circuit that contains each edge exactly once. And let's think about, if that's true, what happens at a vertex of G? So we've got a vertex of G, and there are some edges incident with it. And because each edge must be traversed exactly once, that means that each time we go into the vertex, we must also go out of the vertex. So each time we go in, we must also go out, and we do some other stuff, and then we come back and we go into the vertex again, and then we must exit that vertex again as well, otherwise we'd be stuck. So, in other words, if it's Eulerian, then for every in, there is an out, and therefore, the number of ins in our traversal is equal to the number of outs. And what does that mean? That means that the degree must be even, because if the total number of times that we go through the vertex is k, then we go through the vertex with k edges going in and k edges going out. So the degree of each vertex must be even if the graph is Eulerian. And so that's the end of the first direction. The second direction is actually pretty difficult to prove, and that was the bulk of Euler's paper. In a more theoretical class, we would be doing this proof in the course. However, it's a little beyond the scope of this particular class. It is something that you can find online if you wish, or you're welcome to ask me personally if you would like to talk about the proof of the other direction. So here's one last definition. A connected graph is traversable if there's a trail that visits each edge of the graph exactly once. Again, exactly once is a little repetitive because a trail cannot repeat edges, but in any case, let's think about which graphs are traversable but not Eulerian. So back when we were thinking about the bridges of Königsberg problem, this would be equivalent to walking through the town, crossing over every bridge exactly once, but starting and ending at different places instead of at the same place. So let's think about that. Try to think about it in general, and think about our justification for why a graph is Eulerian if and only if every vertex has even degree. In other words, there's a circuit that contains every edge exactly once, if and only if every vertex has even degree. So pause and think about this just for a moment. Okay, so if the graph is traversable, that means that we start at a vertex V and end at U, which is not equal to V, and that we include every edge exactly once. So this is really similar to the previous problem. In fact, for all vertices besides U and V, the above criteria for being Eulerian must hold. So for all vertices besides U and V, if we have some other vertex W that's not at the beginning or the end, then it still must be the case that we visit each edge exactly once. So again, for every in, there is an out. So for all vertices besides U and V, the degree must be even. So for all vertices besides U and V, the degree must be even. What about the start and the end? Well, if we start at a vertex V, then we're starting at V and we're exiting V, and then we're doing some stuff, and then we're coming back into V and we're leaving V again, and so on. And so we have the case that all the other entrances and exits must match up. There must be an even number of those, but the start is not paired with an entrance. So in other words, the degree of v is odd. It's 2 times some integer plus 1. And similarly, if we think about the place where the trail ends, then we may have gone through u some number of times, and that number of times is an even number of times. But then whenever the trail does end, that end is not paired with an exit. That entrance is not paired with an exit. So again, the degree of u is odd as well. So if a graph is traversable but not Eulerian, that means that there are 2 vertices of odd degree and all other vertices have even degree. So a graph is traversable but not Eulerian if and only if there's exactly 2 vertices of odd degree. So let's look at a graph that has that property. N3 was one of the graphs above that does have exactly 2 vertices of odd degree. This is a degree 3 vertex, and this is a degree 3 vertex. This is a degree 2 vertex, this is a degree 4 vertex, and this is a degree 4 vertex. So according to our train of thought, an Eulerian trail must start at one of the degree 3 vertices and end at the other one. Let's see if we can start there and end at the other odd degree vertex. So if we start there, we could go this way, this way, this way, this way, and we could go up or down, it doesn't matter. Let's go up and over and down and over. And yes, that was an Eulerian trail, or in other words, that graph is traversable, and the trail through that graph begins at one of the odd degree vertices and ends at the other odd degree vertex.